Hello, sir. Have you ever wondered how machines recognize face, detects objects, or even diagnoses diseases from images? The secret behind this is image data mining, a powerful technique that helps extract meaningful patterns from a vast amount of image data. In today's video, we'll explore how image data mining works, key models involved, and implement it using Python. Coming to the, we'll see what is data mining. Data mining refers to the process of analyzing, processing, and extracting meaningful insights from images, which means unlike traditional data mining, which focuses on numerical and textual data, image data mining deals with pixels, textures, colors, and patterns. And these are some of the real life applications. First one is face recognition in smartphones. Uh, and second one is medical imaging to detect diseases. And third one is e-commerce for product recommendations. And these are some of the example images. This first one is face detection, which we use in phone to unlock our phone. And this one is, these are the X-rays that are used by hospital. So coming to the next slide, how does data mining works? The step one is image processing. Raw images often contains noise and validation in size, brightness, and resolutions. Processing helps standardize them. Before applying machine learning models, images must be cleaned and standardized. Some of the techniques are grayscale conversions, resizing, and noise detections. Coming to the step two, it's feature extraction. Extracting meaningful characters from images to help AI models understand patterns. Extracting important elements like edges, shapes, colors, and textures used in applications like fingerprints, recognitions, object detections. And the third one is image classification and clustering. Classification assigns labels to images using model like CNNs and SPMs. Clustering grouping similar images, often using k-means. Coming to the models in image data mining, we use our first one is CNN, which is con convolutions network neural networks, which is also known as CNNs, use it for image classification and recognitions. Architecture includes convectional layers, pooling layers, and fully connected layers. We'll discuss in the next slide. And the second one is SVM, which is also known as support vector machine, works well for binary image classifications. Uh, Example, handwritten pieces recognitions. And the third one is k-means clustering, used to group image based on pixel similarities. Used to group image based on pixel similarities. Often used in medical images and satellite images segmentations. And the third one is PCA, which is also known as principal component analysis, reduces dimensionality of image dataset, which is helpful in uh, compression and visualization of the image. We'll go deep on about the models and we'll go to the Python. First one is support vector machine. SVM is a supervised learning algorithm that works well for binary classification problems and is often used in image classification. We'll see how SVM works. First, it finds the optimal hyperline that best separates the two classes. The hyperplane is chosen to maximize the margin, which is distance between the closest data point to the each class, called support vectors. Coming to the second one is principal component analysis, which is also known as PCA. PCA is a dimensionality reduction technique that helps remove redundance and noise from image datasets. It transforms the dataset into a lower dimensional space while preventing most of the variance. We'll see how PCA works. It standardizes the dataset, means it will normalize the pixel values, and after that it will compute the covariance matrix to find relationship between the pixels. And after that, we'll calculate the eigenvectors and eigenvalues to represent the principal components. After that, it will select the k principal component and transform the data. And coming to the third one is k-means clustering. K-means is a unsupervised learning algorithm used for image segmentation, clustering, and pattern recognition. It groups similar data points into k clusters based on similarities. The steps that are performed in k-means clustering are: first, we'll choose the number of clusters that we will take, and after that we randomly initialize k centroids. We'll take some random number of k centroids, and after that we'll assign each pixel to the nearest centroid. We'll calculate the distance between them, and after we'll compute new centroids based on the pixel average, and after that we'll separate the uh, centroids, and after that we'll repeat the process until convergence. And the coming to the next one is CNN. CNN are types of deep learning model specifically designed for process structured grid-like data such as images. They are highly effective in image classification, image detection, and facial recognition. These are CNN is mostly used nowadays in self-driving cars, which have sensors which helps in detecting objects which are coming in front of us. And the architecture of CNN are first convectional layer, and after that pooling layers. After that, it fully connected layers, activation function, backpropagation, and optimizations. Let's dive into the Python code. We have used minus dataset. What is MNIST dataset? Handwritten digits dataset that contains values from 0 to 9. We have 60,000 training images and 10,000 test images. Each images is 28 into 28 pixel. And I have already run the code, and I have already compiled everything, and I'll discuss one by one. The first one is here I have imported some libraries. I'll discuss some of the important libraries. Here from TensorFlow.keras dataset, we have imported this dataset, and after that we have used K. We are using K means, so we have imported K sklearn cluster, and we will be using uh, PCA, which helps to reduce image dimension. So we have imported in from decomposition, and after that we have also imported Convo 2D, Max Coding 2D, and Flatten and Dense. These are basically used in CNN. And I have sent the dataset to I have separated the dataset into X10 and Y-train, and I have loaded the data. And after that, and I have displayed the some of the sample data which contains their labels, and these are some of the sample data I have shown. And after that, we'll reduce here extend is equal to extend by 255.0, and xtest is equal to xtest 255.0. It helps scale. It will scale them to 0 to 1, which helps us to improve the model's efficiency. Okay, after that pixel values ranges from 0 to 25, dividing by 2255 scales them to 0 by 1, improving model's efficiency. And after that we'll flatten the image into 1D vector for PCA and K-means. Here uh, each image each image is 28 and 28, which is 2D, but machine learning model prefers 1D. So we'll reshape them, which converts images to 784 pixels in a row. And after that, we'll apply PCA for dimensionality reduction. Images have 784 dimensions, which is too high for clustering. We'll reduce it using PCA. We'll apply PCA to the 50 components. We'll reduce the 50 components, and after we'll transform it to the PCA. And here, after applying PCA to the dataset, and this is what I have got. And also I have applied k-means to them. And after applying k-means, we'll assume 10 clusters for digit 0 to 9. K-means dot fix Fit XPCA finds patterns between images. And I have shown you the histogram of the following dataset. This histogram shows shows how images are grouped into clusters. And the next we have done the CNN for classification. Here Convo here Convo 2D 3233 detects features from images, and Max Volume 22 reduces image size, and Flatten converts images into a 1D vector, and Dense 128 help fully connected layer, and Dense and Softmax outputs probability for 10 digits. After that, we will be evaluating CNN performance. In this, we have given five epochs. Accuracy. Uh, okay, here we have calculated the accuracy and loss. First, this is the model's accuracy. This graph shows how CNN performs our epochs. In machine learning, an epoch refer to one complete pass of an entire training dataset through the model. In this graph, we analyze the performance of our model during training by observing accuracy and loss for both the training and validation sets. In graph 1, the X represents the number of epochs, the Y represents accuracy and how well the model performs. The blue line here represents training accuracy, and the orange line represents here validation accuracy. Initially, the training accuracy uh, increases rapidly, and then it stabilizes near 99%. The validation accuracy follows a similar trend, but it's slightly lower, indicating the model generalizes well, but could still have some overfitting. And also, we have performed model loss. Here the X accuracy represents the epochs, and the Y represents the loss. The blue line represents training loss, and the orange line represents the validation loss. Initially, training loss decreases rapidly, which means the model is learning. The validation loss also increases, but not as sharply as training loss. And at the last few epochs, it slightly increases, indicating possible overfitting. And this is what we have learned from this data set after training them. And coming to the conclusion, the model have high training accuracy and low validation accuracy, indicates it has learned well. However, since the validation loss slightly increases at the end, we might need to use techniques like dropouts, regularization, or more augmentation to reduce overfitting. And coming to the conclusion, so we have reached the end of our journey into image data mining. Through this session, we explored how machine learning helps react meaningful insights from images. Let's quickly summarize what we have covered today. First, we covered the fundamentals of image data mining, and why it is important in fields like medical images, imaging, security, agriculture, and social media analytics. Then we explored various machine learning models, including CNN, K-means clustering, SVMs, and PCA, and how they help with tasks like image classification, segmentation, and feature extractions. And of course, we got hands-on Python with implementing K-means clustering for image segmentations and a CNN for classification. As technology evolves, the impact of image data mining is growing rapidly. It's now a key component of innovations in self-driving cars, medical diagnosis, smart surveillance, and automated content moderations. Thank you.